Now we will take our discussion further. We'll talk about that in case if you assume some other linear unbiased estimator apart from the OLS estimator, its variance is going to be higher. So let me just put the point which I'm trying to say. So supposedly if you have the sampling distribution of beta 2 hat like this, right? So this is what your beta 2 hat is. And at this particular point, your E of beta 2 hat is equal to beta 2 is there, right? So this is what the sampling distribution of beta 2 hat looks like. Beta 2 hat is an OLS estimator, right? Now, you can also just see some other estimator, beta 2 star. And you have something like this. So E of beta 2 star is also equal to beta 2. Sampling distribution of beta 2 star. Mhm. Both of them are unbiased. E of beta 2 star is also equal to beta 2. E of beta 2 hat is also equal to beta 2. But beta 2 hat is less diffused around its mean. Uh, so if I just want to put beta 2 hat also on the same diagram, it will somewhat looks like this, right? It will somewhat look like this. So if I just want to put beta 2 hat also on the same diagram, then it looks like this. So this is beta 2 hat. Uh, and this guy is beta 2 star. Both of them are linear, both of them are unbiased, but the this beta 2 hat is less distributed around its mean, right? So it is uh, the distribution of beta 2 star is more diffused around its mean. So you can just write this. The distribution of beta 2 star is more diffused or widespread around its mean, right? Than the distribution of beta 2 hat. So basically, you want to say that the variance of beta 2 hat is less than equal to the variance of beta 2 star. Beta 2 hat is what the OLS estimator is. Beta 2 hat is what the OLS estimator is. So given that both the estimators are linear and both of them are unbiased, so you will be choosing the estimator which has a lesser variance, right? Which is more precise, right? So you are likely to choose the one which is which is much more uh, uh, nearer to the mean instead of much more diffused around its mean. Uh, so, one more thing is this theorem is not making any assumption about the distribution of the error term, right? So, in case if it is not making any assumption about the distribution of the error term, it is also not making any assumption about the distribution of yi, right? So, probability distribution of this. So, please just write somewhere that Gauss Markov theorem does not make any assumption about the probability distribution of the random variable ui, and therefore yi. So as long as the assumptions of CLRM holds, this theorem holds. So this theorem holds, right? This theorem holds. So let me just put it this way. So beta 2 hat is summation of ki capital yi. And ki's are what? You have just seen that in the earlier recording. Xi upon small xi upon summation of small xi square. So basically what beta 2 hat is, it is the weighted average of yi's with ki serving as weights. Beta 2 hat is a weighted average of yi with ki serving as weights. So now let us define our alternative estimator apart from beta 2 hat, some other linear unbiased estimator. So let me just define that. So let us define an alternative linear estimator beta 2. So let's say beta 2 star is summation of wiyi. हाँ बेटा. So E of beta 2 star is E of summation wiyi. Well. So can I just write it like this? Ta 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 ta. Summation of wi. E of yi. But what is yi? Beta 1 plus beta 2 xi plus ui, right? It's going to be like this. Well, um, this guy, E of ui is going to be 0 beta. E of beta 1 is going to be beta 1. So it is beta 1 summation of wi plus E of beta 2 is beta 2. Huh? And this is going to be just summation of wi capital xi. Huh? Because these are the stochastic terms, non-stochastic terms. So they'll come out of the expectation. And E of ui is 0. है ना? That is 0. हाँ बेटा? Now you tell me if you want E of beta 2 star to be equal to beta 2, what conditions you have to put on summation of wi and summation of wi xi? You have to say that summation of wi should be 0 and summation of wi xi should be equal to 1. For beta 2 star to be unbiased, because you want that for beta of, because you will be, this is in the class of minimum linear unbiased estimator, so it is linear and it has to be unbiased also. So for beta 2 star to be unbiased, you would need summation of wi to be 0. And summation of wi xi equals to 1, and summation of wi xi equals to 1. What is variance of beta 2 star beta? What is variance of beta 2 star? That is E of beta 2 star minus beta 2 ka whole square. That is what it is. So what will that be equal to? That is variance. And beta 2 star is what beta? This guy? Summation of wi yi. So, है ना beta? It is going to be like this. Now you tell me one thing. What is the variance of this? A square variance of x. That's a property of variance. है ना? That's the property of variance. So wi's, these are constants, like, so this will be what? Summation of wi square variance of yi will be like this. है ना? Acha, then you said that yi is equal to beta 1 plus beta 2 xi plus ui. Beta 1 plus beta 2 xi is a deterministic term. So that's, there's not much change in that. So the variance of yi is going to be dependent upon variance of ui. Beta, that's what you said now. So that's a non-random component. This is the random component. So its variance is going to be dependent upon this. So variance of yi would be equal to variance of ui, and variance of ui is sigma square, homoscedastic variance. Uh-huh. So you have this sigma square summation of wi square. Achha, can I write it like this? Minus small xi upon summation of small xi square plus small xi upon, I can write like this. I can write like this, na? I hope you guys are following me. Mm-hmm. Havita, I have put this in the parenthesis. So it is a plus b ka whole square formula. So what will that be? Sigma square summation of wi xi upon summation of small xi square ka square plus sigma square. This is a beta. This is b. Don't write this ab. I'm just telling you this. So it is a plus b ka whole square. So a square plus b square plus 2ab. What is b square then? Summation of xi square upon summation of xi square ka square. So this thing is going plus 2 sigma square plus 2ab. 2 will come out of this, the summation sign. So it is what? wi minus xi upon summation of small xi square Ha beta? It is going to be like this. Now just look at the third term first. Just look at the third term first. Huh? Just look at this term now. I'm just looking at the third term first. So we'll start again with this, but let's just look at the third term first. So if I'm just going to open this up, wix small xi upon summation of small xi square minus this thing into this thing, summation of xi square like this. Have it. What is small xi? Capital Xi minus x bar. Mm-hmm. Wi capital Xi minus x bar summation Wi on summation of small xi square. Beta, you have just said here that summation of Wi should be equal to 0 and summation of Wixi should be equal to 1. That's what you have said. So this should be equal to 1 and this should be equal to 0. Right? So what is it that you have now? It is 1 upon summation of small xi square minus 1 upon summation of small xi square. So that is equal to 0. So basically what you're trying to say is this entire term is nothing but 0. This entire term is nothing but 0. So you're left out with only this, right? You're left out with only this. So variance of beta 2 star is what beta? Sigma square summation of, sorry, small xi upon summation of small xi square, right? Hmm. Tell me one thing. What is this? This you have already done. This is variance of beta 2 hat. You remember now from our earlier recording? That's what you have proved, beta. Variance of beta 2 hat is sigma square upon summation of small xi square. That's what you have done. What is this? These are nothing but the weights of uh, your uh, your OLS estimates. So variance of beta 2 star is equal to sigma square summation of, sorry, hmm? Now you tell me one thing. This is the weight of non-OLS estimator. This is the weight of OLS estimator. Hmm? So if Ki is equal to Wi, then variance of beta 2 star is very well equal to variance of beta 2 hat only. This means that this beta 2 star was nothing but the OLS estimator only. If this Ki is not equal to Wi, whether it is lesser or more, whatever it is, then this is going to be a positive term. Hmm. This is going to be greater than this guy. So variance of beta 2 star is something positive plus variance of beta 2 hat. So in all, you can say that this non-OLS estimator, even though it is a linear unbiased estimator, I mean it has the variance which is more than the OLS estimator, right? So it means what? It means that it is better. So these OLS estimators, they have the minimum variance in the class of all linear unbiased estimates. So this variance of beta 2 star means the variance of the non-OLS estimator. So something which is not OLS, right? Alternative linear estimator. Uh, and variance of beta 2 hat is OLS estimator. So you're saying that the variance of the OLS estimator is less than the alternative estimator, right? Even though it is linear, even though it is unbiased, but the variance of the other than OLS estimator is more, right? So this is what Gauss Markov theorem is. So you have to do these two recordings in order to understand completely Gauss Markov theorem. Thank you, Beta.